Hi again, everyone. So we're going to continue our program over the next 45 minutes. Zahra Ronaghi is going to talk about high performance data science with RAPIDS. Zahra, please take it away.
All right, so hey everyone, my name is Zahra Ronaghi. I'm a data scientist and software engineer at NVIDIA on the RAPIDS team, mostly focused on machine learning and cloud integration. So today we'll just go through some of the fundamentals and core libraries of RAPIDS, and then we'll have some time at the end for questions. And feel free to add anything in the chat too, and we can get to them at the end. So what is RAPIDS? At a high level, it's an open source software suite of libraries that are designed to accelerate data science by running the entire pipeline on GPUs. It started at NVIDIA, but it's an open source project. So there's a lot of other groups that are working with us too and contributing to the code. I'll talk about how we're trying to avoid extra copies or communication to host and how we're trying to accelerate end-to-end workflows. And then I'll cover the building blocks of this framework or platform too, mostly focused on data frames and machine learning, but I'll briefly talk about graph analytics too. So looking at the data processing evolution, we've been using Hadoop for handling large distributed files. But one of the downsides with that is that you have to read and write from and write to HDFS for each part of the work or the job. So you end up with two IO barriers that can reduce the total or have an impact on your total runtime. So then after that came Spark, which tries to hold everything in memory to eliminate these IO barriers. You end up with faster processing since it's reading straight from memory instead of HDFS at each stage, and then you'll end up in a reduction of total runtime. So, but we can also do better than that. So if we process some of these libraries on GPUs, we can accelerate them. So we needed something to accelerate how we process data and do traditional machine learning. So we've been working on accelerating these pipelines and computations on GPU, but we were still spending some time on read and write to host or CPU memory. So again, you'll see for each part of this, if we're running a query, and then let's say ETL and machine learning, we'd have to load our data from CPU to GPU, write it back, and then load it again. So I have a diagram to just show what was initially happening and why. So let's say we have two applications. One can be for machine learning and app B, for example, for visualization. Both of those use GPUs today. They offer great acceleration. However, after data gets loaded to GPU and after processing, we had to copy back to host memory. And we have to change our formats on CPU, then copy again back to GPU for another application. And so this is what was happening with traditional analytics. We'd have to copy and convert data formats because these libraries couldn't directly communicate on the GPU. And this just caused too much back and forth movement. So what if we could keep our data on the GPU and eliminate this communication overhead? So when data gets loaded for app A, and app A and app B, for example, could communicate and pass data around, we should be able to leave data on the GPU and concatenate a bunch of these operations together to remove too much movement. So as a result, we can then accelerate the whole end-to-end pipeline and remove these extra copies and converts. So this is actually what led us to Apache Arrow. So very briefly, high level, if you're not familiar with Apache Arrow, what it is basically a language and hardware agnostic caller data structure. And it's interesting for CPUs as well because it'll allow you to run these operations without serialization and deserialization. So for RAPIDS, what we wanted to do is we wanted to implement a mostly Arrow-based memory model on the GPU as well. And the great thing about this is if there are other libraries and applications that can also read and support the Arrow format, now they can read directly from pointers on device rather than having to copy data back and forth. So let's say if you wanted to use one of the libraries in RAPIDS, and if you already had a workflow in PyTorch, now again, you'll be able to pass data without an extra copy to CPU. And that's because PyTorch also supports this format. So where we see this data process evolution going is not just eliminating IO bottlenecks and PCIe bottlenecks, but we're trying to also eliminate bottlenecks of serialization and deserialization between different libraries. So overall, depending on data and algorithms, we've seen up to 50 or 100x improvement, which again depends on the data and application too. And I'll talk about a couple of the benchmarks in the next few slides. But basically, if you have applications that are able to use common memory formats and pass references back and forth between APIs, you can get huge performance improvements. And so the traditional PyData ecosystem looks like this. We can use Pandas for data cleansing, exploration, analytics, scikit-learn for machine learning, NetworkX for graph analytics. And then you can also scale these with Dask. And comparing this to RAPIDS, this is what the software stack looks like. So like I mentioned earlier, we built it on top of Apache Arrow. So you see here Apache Arrow at the bottom. And the reason is it's a bridge between all of this traditional big data and this new GPU accelerated platform. And it's, like I said, it's basically a way to store data. In mostly tabular data has been stored row-based so far for a lot of different applications like databases when you have records of data, which makes sense. But for analytics, when you want to be able to pull columns of data instead of scanning all rows, it's much more efficient if you also store them in columns. And so it's created a way to pass data around between different software. So then on top of that, we have three core libraries, cuDF and cuIO, which are our analytics libraries, similar to Pandas. So if I compare these two charts, and then cuML for machine learning, and then finally cuGraph for graph analytics. And you see Dask up here because that's what we use to scale up and scale out. And like I said, the best part, well, I probably didn't mention this, but the best part of this is that all of these libraries are in Python. So you can use a Python API and you don't have to worry about writing CUDA C++ code. So you'll see that when we get to the examples and the software stack for each of these two. So a couple of benchmarks. Here's the first one that we published, which was, I think, almost 2 years now. This is the first one that we did with XGBoost and cuDF and RAPIDS. It's a mortgage workflow from Fannie Mae. Every month they put out a file that contains mortgage that was given, debt to income ratio of the customer, where they live, how well previous mortgages are doing. And what we did, we loaded 200 gigabytes of data, used XGBoost to train, and then ran a predictor on other mortgages that we didn't have information about. So the top of the charts for CPUs was using Spark. And then we use RAPIDS on the DGX2, which is 16 V100s, and also 5 DGX1s, which is 40 V100s, which were hooked together with InfiniBand. So it took about 3 minutes to train on a DGX2 and about half an hour on 100 CPU nodes. And so if we look at the end-to-end, in general, everything ran in about 200 seconds. So we were able to load the data, prepare the data set, train and predict outcome faster than we could even get the data loaded and ready on the CPU for the next step. So the reason that I talked about that, which was again published about 2 years ago, is to just show improvements over time too. So you can see this is RAPIDS version .2 and then .10, 15, and right now we're at 16. So it shows improvement and optimization over time too. We're adding functionalities and algorithms with every release, but we still profile and figure out where else we can accelerate and improve on. So like I said, the current release is 16, which was actually released last week. But in .15, which is the one here, we added support for the latest GPU, which is Ampere or A100s. Okay, and this is another benchmark, which is TPC-XBB. It's a standard big data benchmark that includes ETL and data processing, plus machine learning workflows. And we were able to outperform the latest record by 20x. We ran this on 128 A100s. Took about 15 minutes compared to the top result, which was 4.5 hours on the CPU system. So if you go to the website, you can just see what the top runs are today. We use cuDF for ETL, cuML for machine learning, and then Dask plus UCX for communication across nodes and GPUs. We've also enabled Dask to use main memory and spill from GPU to CPU for some of the larger workflows. So this means we can also use CPU memory as temporary storage if we need it. Okay, so the 3 core libraries, like I mentioned, cuDF, and we get asked this question too, that do we actually need a GPU accelerated DataFrame library? And the answer is that we've seen average data scientists and engineers spending up to 80 to 90% of their time in ETL. So feature engineering, data cleansing, as opposed to where they would want to spend their time in fine-tuning and optimizing their models. So if you can reduce this data processing time, you'll have more time to explore different models and then fine-tune them. So cuDF is our DataFrame library that can accelerate loading, filtering, manipulation of data. If you're accustomed to importing libraries like Pandas, this is pretty much the same. So it's like a drop-in replacement, and then you can call functions that again are very similar. So it has a Pandas-like API. And looking at the software stack on the right here, so you'll see the C++ level library, which is called libcuDF. You can use that directly. But then we also, on top of that, we have our Python bindings, which is cuDF. And that's the interface to C++ that mimics the Pandas API. Anywhere that it doesn't, it's something that we're working on. And then at the top, you'll see Dask cuDF, which I'll talk about if we have some time at the end. But we're using Dask for distributing larger data sets across nodes and GPUs. And then here, cuIO, which is part of cuDF. But we have GPU accelerated reader and writers for some of the different file formats like CSV, ORC, and Parquet. This will also support all types of decompression. So if you have a CSV file, let's say if it's gzip, EZ2, or other format, then you can directly load that onto GPU, decompress, and start ETL right away. And so this is just the different readers and writers with every release that we added them. Like I said, for example, if you wanted to read a CSV file, you'll see here that it's very similar to Pandas. You'd import cuDF. And then here, let's say you wanted to just count the number of rows in that data. You can load it into the GPU memory and then compare how much it took on CPU versus GPU. And then another part that we're working on, other than this, is we're trying to integrate with GPU direct storage to maximize I/O throughput and reduce I/O bottlenecks too. We're working on moving these pipelines to GPU. So traditionally from storage, you have to make a copy or a stop through CPU. And we're trying to avoid this extra copy and make a direct path to GPU. So now you're still using CPU to set up the computation, but then most of the work and data movement will come straight to GPUs from storage. Okay, so another benchmark which compares cuDF and Pandas. So this is cuDF.13. We set up basic data frames with 2 key columns and valid columns. For some of the common operations like merge, sort, group by, we can see the performance, so 300, 500x. And then again, depends on the size of the data frame too. So with more rows, we get better speed up. And then here's a mention of the RMM pool allocator. I won't go into details, but this is the RAPIDS memory manager, which is basically a pool allocator to make CUDA device memory allocation and deallocation faster and asynchronous. This is just worth mentioning because it's where it really helps us with optimizing a lot of these workflows. And then string support, we added string support in cuDF recently. Initially, it was a separate library, but we migrated those functionalities into a more user-friendly DataFrame APIs. So we also adopted the Apache Arrow format for strings, which resulted in more efficient memory use and speedups. So now we have support for tokenizers, upper, lower, concat, splice, and more. And this will also enable complex string and text manipulation too for some of the NLP applications. And then finally, another thing that we've been working on and aiming for is interoperability. We don't want to reinvent the wheel. We're working on mimicking existing APIs. We're not trying to replace existing libraries, but we're more focused on complementing those. So for example, if you have a deep learning focused workflow in PyTorch, and if you want to use cuDF for pre-processing, you can do that. And then you can use the cuArray interface to go between these libraries without extra copies. So what cuArray interface is just a standard format to describe a GPU array and that allow it for sharing between different libraries without copying or converting data. So just like you can work with NumPy and Pandas in the same workflow, you can use cuDF and cuPy together while keeping the data entirely on the GPU. And then finally, the current version of RAPIDS, which is 16, we've added support for more data types, and we're continuing to improve on RMM and more data frame operations in CUDA optimizations. Okay, so let's talk about machine learning. Like I mentioned, the goal is to be able to import a GPU library, for example, cuML, and then run machine learning algorithms on GPUs without having to write CUDA C++ code. So of course, sometimes it's just as easy as just changing that import, and sometimes it requires changing few parameters and keywords too. So that's our final goal. We want to leverage existing code without replacing them. So the vision of cuML is a GPU accelerated version of scikit-learn. Again, the API is very similar, and then you can also use cuDF data frames as input. So let's look at the software stack again. On the right, the top layer that's exposed to the user is Python. Underneath that, we have Python, wrapping C and C++, and that connects the C++ to Python. Our core algorithms are built in a combination of existing CUDA libraries, for example, Trust, cuSparse, cuSolver, and the machine learning primitives. So these ML prims are basically the building blocks of basic operations that make the bulk of machine learning. So you can think of them as core linear algebra, distance functions, matrix multiply, norm, transpose, and things like that. So another thing that we're working on is wrapping these primitives in Python too. So if you're working on some of these techniques and algorithms that are not on our roadmap, then you can do that again with taking these building blocks and composing them into a new algorithm. And then of course, all of this at the bottom connects to CUDA too. And we use Dask for distributed training across multiple nodes and GPUs. And so here's an example of a CPU-based clustering. Let's compare this with cuDF and cuML. So we can port to GPU with just importing these two libraries. It's very common that with a lot of our core algorithms, but I'll just say this up front, you might see a deviation in some of the other examples, or some of the functionalities may not be fully supported yet. And then sometimes we have additional parameters. For example, how much GPU memory you want to use, but usually they're very similar. So let's look at the performance if you were to do that, and if you were to port some of these CPU codes to GPU. We've seen ranging from 10 to 20 to 100x faster training on a single V100 compared to dual socket CPU, depending on the number of features that were used. And again, more data will usually give us better speed up because we're fully utilizing that GPU. And this new library, also the Forest Inference library. So after you train it, you want to run inference on GPU 2. This was actually released, I think it was RAPIDS.19. So what it can do is, for now, it can just accelerate prediction for random forests and boosted decision trees. So it can take either data stored in CPU memory, like NumPy arrays or GPU arrays. And what it does is it takes a saved model, loads it, and it allows to run inference much faster. So for larger models, again, we've seen 23 or 36x speed up on a B100. And then XGBoost, since this is the first benchmark that I showed you, and the first multi-node, multi-GPU ML algorithm that we had, XGBoost was already supported through DMLC, and they had support for multi-GPU. So we've been working with that community to add multi-node support too. So now XGBoost can load data from cuDF and cuPy directly. So before this, if we wanted to use cuDF, we'd have to load our data, do some of the pre-processing, write it back to CPU, and then load it into XGBoost. But we work with it closely, so now you can just directly use cuDF. And again, it goes with all the same format that we want to be able to use the end-to-end workflow. And so now it also has a Dask API that you can use to scale up and scale out. And the difference compared to the rest of the cuML algorithms is that for those, you need to import a different library. So you import cuML instead of scikit-learn. But in the case of XGBoost, what you do is you just change one parameter. And by changing that, you're able to train on GPUs. So again, we've also integrated RAPIDS Memory Manager recently. And with that, we were able to decrease our memory use by 2/3 too. Another part that we've been working on is hyperparameter optimization, which is basically a search on the hyperparameter space to find the parameters for the best model or higher accuracy. So what we've done is we're integrating with HBO tools like RayTune, MLflow, Aptuna. And for example, MLflow, if you're not familiar, it's basically designed to snapshot your training code, metrics, and train models. And then you can query these results later and find the best model to deploy for production. So the nice thing is, since it works well with scikit-learn and our API is similar, it works with cuML out of the box too. And along with that, we've also done this with every cloud. Like I said, the nice thing is you can run through different hyperparameter options pretty quickly to find the most accurate model for your problem and data set. So we were able to train 25 times faster and with 7x reduction in cost, for example, on Azure ML. Okay, so looking at some of the algorithms that are available today, at the top, again, gradient boosted decision trees, which is XGBoost. And then some of the other ones that are currently supported on multi-node on multi-GPU are random forest, k-means, KNN, PCA, SVD, and other ones like dbScan and logistic regression are single GPU, and we're working on multi-GPU implementation. I should also mention that if there are algorithms that you want or are working on and you don't see them in this table, let us know, or you can go to GitHub and submit a feature request. And this is what we're working on. So by the end of this year, as we continue working on this, we're working on adding more multi-node and multi-GPU support for most of these algorithms. And then one more thing before I get to cuGraph is the model explainability accelerator for SHAP. So this is coming soon. What we're doing is we're building tree SHAP to interpret these decision tree models. So we're often producing hundreds or thousands of these trees. And a lot of times we want to be able to explain how or why we got to our results. So what we can do with SHAP is we can explain single predictions with a force plot, which you can see here. So it's not a black box anymore, and you can see what all is inside, which it'll also show you some of the contributions of different features, which ones the model picked to make those predictions based off of. Okay, so just a few slides on cuGraph. What it is, it's a collection of graph algorithms. We've taken NVGraph and moved it over to RAPIDS, but we're also adding more algorithms. And what cuGraph actually does, it unifies the GPU accelerated graph analytics libraries like NVGraph, Gunrock, and Hornet. We're collaborating with few groups at universities. And the interesting thing about graph is that it's very dependent on interconnects. So once you start spreading them out, it slows down and can decrease your overall performance. But it's also a good use case for NVLink, which is high-speed GPU to GPU interconnect. So with our initial benchmarks compared to NetworkX and CPU, depending on the data, again, we've seen up to 500 or 1,000x improvement by also loading and processing the graphs on GPUs too. So using cuDF to load the data, do some of the pre-processing, and then cuGraph for graph analytics. And then similar to the other libraries, we want to make it easy for NetworkX users to use cuGraph. So the API is very similar to NetworkX. And again, very briefly, the software stack. At the bottom, we have CUDA. On top of that, the CUDA libraries. And then some of the primitives and core frameworks. From those, we build the cuGraph algorithms, and then Python, and then finally the top layer, which is the Python API. And these are just some of the benchmarks of PageRank, which is one of the popular graph algorithms. It's a measure of relative importance between links and connections. So for this benchmark, we use different RMAT data sets and scales and ran this on a DGX2 with 16 V100s that are connected through NVLink and NVSwitch, which is basically 300 gigabytes of GPU to GPU bandwidth. And then we compared this to 100 CPU nodes using HiveBench benchmark, which took about an hour and a half compared to the 30 seconds on 16 GPUs. Okay, and then these are the available algorithms in cuGraph today, like PageRank, breadth first serve, single source shortest path, mostly running on single GPU. And what we're working on for the next version is adding multi-node and multi-GPU support for most of these. Okay, so now if you're interested to try this, this is how you can access the software. The RAPIDS container is available on NGC, which is NVIDIA's container repository, as well as Docker Hub. For bare metal installs, you can install through Conda, and it's usually the easiest way to install on your machine. We also release nightly builds. So if you want to work on the latest development branch, and if you don't want to build it every day, you can just pull the nightly release. And then you can also download all of this from GitHub and build from source, since it's all open source. And then here's an example of the interactive installation guide, which I really like and use frequently. If you go to the website, which is rapids.ai, you can choose your method, release, packages that you want to install, and then you'll just be able to copy the command at the bottom and install all those libraries that you need. Here's the GitHub link. So you can access the repositories for all these libraries, as well as some of the additional ones that we've worked on, like cuSignal and cuSpatial for signal processing. And there's also a lot of notebook examples. So if you're interested to look into some of the single GPU or multi-GPU examples, there's a lot of demos with different data sets, use cases, and these are usually good starting points. So when we present at workshops and conferences too, we try to upload everything to this repo. So you can go and look through those. There are a few prerequisites for running RAPIDS either on bare metal or in a Docker container. So you need Pascal or newer GPU architecture. So Pascal, Volta, or Ampere. And then CUDA, we right now support CUDA 10.1, 10.2, and 11 with the compatible NVIDIA drivers, and then Ubuntu and CentOS, and then the Docker versions if you're using Docker images. And this is just an example of some of the collaborations we've done with research groups at Oak Ridge National Lab. One project which was focused on COVID-19, and Orionel presented this at GTC a couple of weeks ago and published a blog actually yesterday. So they're looking for the right chemical structure that binds to the viral protein and prevent it from attaching or replicating. So to screen drug candidates, they need to screen billions of molecules. and they're using a software called Autodoc on the GPU, which will allow them to evaluate these molecules about 200 times faster than CPU. So they're running this on all of Summit, which is about 27,000 B100s. And what they were able to do is monitor more than 25,000 molecules per second. And then what they're doing with RAPIDS is they're using actually Blazing SQL, which is a SQL engine that's built on top of RAPIDS. And they're trying to organize, search through, and analyze terabytes of data that are generated by Autodoc. So this will give them the ability to create an interactive analysis tool for querying and analyzing all these data sets, which they weren't able to do with conventional and persistent databases. So now they're able to run through these within minutes, which would take days previously on the CPU. And if you're interested, feel free to join our Slack channel or add any issues, PRs, feature requests on our GitHub. There's a lot of conversation that goes on our Slack too, so you can just join that and ask any questions, or if you need help with running anything, we can help you on that channel. And then very briefly, I have a few slides on Dask, since I mentioned this a couple of times, and we use this to scale up and scale out on multi-node and multi-GPU. So it's a pure Python API. If you're not familiar with it, it's a pure Python API and pure Python API scheduler for working with distributed computing. So it's also an orchestrator that can coordinate all the work that's happening in a distributed fashion. And we use it with cuDF, cuML, and cuGraph. And what is more into what is Dask, and I'll talk about why we started with it. So some of the benefits of Dask is it's a distributed scheduler, like I said, with a Python interface, and it's built to scale Python workflows. The nice thing is it works on your laptop, and the same code can work on a supercomputing cluster. So it's very modular, meaning it separates scheduling, compute, IO, and other things, and you can test all these components independently. So you can have multiple workers on a given node, and you can use one worker per GPU, which is great for GPU utilization. And then all these workers communicate with each other to share data, and it removes central bottlenecks for data transfer. So why did we start with Dask? It's a PyData native, and it's used by a lot of data scientists. It allows single-threaded Python libraries like Pandas and NumPy to leverage all CPU cores. So since it uses existing Python APIs and data structures, it's really easy to integrate and switch between Pandas and scikit-learn to their Dask equivalents. So like I said, it can be deployed in different environments, whether it's HPC or on the cloud, like some of the examples that I showed you on the HBO work. And then it also supports complex scheduling, which is necessary for some of the sophisticated algorithms used in machine learning, image processing, and statistics. So data locality is already baked in to execute all these computations where data lives and minimize network traffic to improve your overall efficiency. So what we did was we took the same exact paradigm and wrote it to leverage GPUs. And now it'll allow you to partition Python jobs across multiple nodes in multiple GPUs. And so this is some of the recent work that we've done and how we're getting some of the good performance that I mentioned earlier about TPC-XBB. Traditionally, Dask uses TCP to communicate. It's a Python native, and TCP is usually the standard way that a lot of these Python applications communicate. So we know TCP is reliable, but it can also be slow. So communication becomes a bigger bottleneck as we accelerate our computation. For example, when we use GPUs for computing and we're accelerating these libraries, we don't want to be bottlenecked by the communication. So we're working with the OpenUCX project, which what it does, it provides a uniform API around different high-performance networking libraries like InfiniBand, but also the traditionally network protocols like TCP, and also GPU-specific protocols like NVLink. So it can figure out which networking system to use based on the hardware. So to get high performance networking in Dask, what we did was we wrapped UCX with Python and then connected that to Dask. So this led us to create UCX-Py, which is a Python wrapper around the UCX-C library, and it provides a Pythonic API. So now Dask can scale on GPUs and CPUs with hardware-aware communication. And just to give you an idea of what this looks like, let's say if we look at Dask visual dashboard, which will look like this. This is an example of running a matrix decomposition workload. And this dashboard, there's different colors that mean there are different parts of the workflow. So if we look at the top chart, there's a lot of red, which means that's the communication. And that actually makes sense for distributed matrix decomposition, since you'd have to send matrices around. It's expensive and it takes time. So what the bottom chart is the same workload, but now with UCX. So similar computation, but then we can send all these matrices around much faster. And this is one of the reasons that we're super excited about Dask plus UCX. And so with Dask in UCX, what we can do is, so first, just RAPIDS will allow you to scale up your workloads on single nodes or machines with the same API from the Python ecosystem. So we talked about if you're using NumPy, now you can use cuPy on the GPU. Pandas you can import to GPU with cuDF, and then some of the other examples. And what you can do with Dask is now you can take the same ecosystem and run it on multiple nodes in larger scale problems. So Dask already scales CPU libraries that could be, so it's used for multi-core and multi-node scaling. And similarly, we can run RAPIDS plus Dask on GPUs. So as long as the APIs are similar, these will also look similar to Dask. And just a couple of examples of how this looks. So Dask combined with RAPIDS and cuDF in a clear way. So if we look at the Pandas example, we can have many CPU data frames, combine them with Dask to form a distributed CPU data frame. So you get Dask orchestrating a bunch of Pandas data frames. And for example, in this case, each Pandas data frame has a month of data. So comparing that with cuDF, it's exactly the same. Just instead of Pandas, Dask is now orchestrating a set of distributed and independent cuDF data frames. And the same works with cuPy and NumPy. So just a couple of things on Dask, and these are the last few slides, is that we want to use Dask to actually produce task graphs. And that's usually the first step. So these are graphs that encode our workflow to a simple format that can then be used to isolate execution from what's going on to actually happen. So we can define a series of tasks and then later execute them. So users, what they'll do in the first step is with Dask, they can produce these graphs, and then the scheduler will execute the graphs that we've defined. There are many schedulers too. The one we use is a Dask distributed scheduler, which is a centrally managed scheduler that can coordinate work between 1 to 1,000 workers across machine, and it lets us execute our workflow efficiently on GPUs. So if we look at this example, if you were to take a simple workflow in this case, we can just create some data with NumPy, let's say a vector of ones. And then we could do the same thing with Dask, except when we do this, it's just creating a graph. So far we haven't created the vector of ones yet. We've just created these tasks, and we know that we're going to create 15 elements in our vector. And then we can define a chunk size and figure out how many elements we want in those chunks. So then we have this distributed vector, and we can spread this across 3 partitions and 3 chunks because we have 15 elements in this case. And the same way we can do it for a more complicated graph too. The bottom task is the same one. We're creating distributed vectors, and then we'll call sum on all of them. And after we run the sum, we have to aggregate and do a reduction step, and we get the final result. And you can do this for more complex task graphs too. So this is just to show you that we started from simple vectors, and this is a machine learning workflow. The great thing about Dask is it actually has really nice visualization tools too, which I'll show you in the next couple of slides. So we use these debugging tools and dashboards to help us understand what's actually happening. And in this case, the red means that task has to be held in memory. So if we look at here, it needs to be used later. And then what we can do with that is we can keep it in memory and use it for later tasks. But the middle blue square, which is here, it shows that we didn't need that data after we finished some of the tasks. So just to give you an example of this will give you a good, it can be used as a profiling tool too. And then Dask can execute this graph, like I said, after we created it on parallel hardware like GPUs, and handle garbage collection and freeing memory for us efficiently. Okay, so this is what this workflow would look like once we execute that and start distributing it across multiple nodes and GPUs. And then finally, I talked about all of this, but to just give you an idea, if you were to just load a CSV file, and then when you call persist, that's when actually Dask is implementing that task graph that I mentioned. And in this case, we just wanted to count the number of rows in that data frame, for example. So if you use Jupyter Lab with the Dask extension and NV dashboard extension, now you can see your GPU utilization. So in this case, it was running on a DGX1 with 8 GPUs. You can look at your GPU memory and then the task streams and what they're doing for each part of the job. So if it was a machine learning workflow, you would see one part that's loading the data, then running the algorithm for training, and so on. So these two might look similar. If you were not using this, you can just run NVIDIA SMI command and check your GPU memory and utilization, but this gives you a nice visual and it's really interactive too. All right, so that's all I had for today. And I'll pause here and take any questions.
Thanks a lot, Zahra. It was a very nice presentation about the capabilities we can leverage with all what you have developed. So questions from the audience. Feel free to unmute yourself and ask your question. Okay, let me ask you one, since this captured my attention from what you presented on Summit. What was the way forward to deploy this framework on the supercomputer? And did you have a baseline for comparison with other methods about how efficient this approach was?
Yeah, that's actually a good question. So comparing this to some of the other workflows, what we did eventually was we ran the TPC-XBB benchmark that I mentioned earlier on Summit. I think we have those results up. I have to check if they were released or not. But so we compared that on Summit compared to, like I said, the latest CPU implementation too. And the nice thing is, well, other than that, because it runs now on Power 9 systems too. But the good thing is, since it's all open source and you can just download everything and get started, what happened was the research started on GCP, and then we got in touch with the researchers and they moved that workflow to Summit, and then we were able to get it up and running within a matter of days. Like I said, it really depends on what you're using today. If there are some of the algorithms that we've already implemented, how complicated that workflow is. But it's something that we're happy to work with you. So if you have questions, like I said, feel free to ping us on GitHub, on the Slack channel, and we can talk to you more about it.
Thank you. Any other question?
I just see a question on the recorded video and slides.
All right, so is it possible also for you to share your slides so that we can post them on our center's website?
Absolutely, yeah, I'll share it with you after the workshop today. And then the ones on installing RAPIDS, yes. So those will also be in the slide deck. And I'll try to add more links in the presentation too. So if you just want to click on that and go to the interactive tool to just choose the libraries that you want to install, and you can just copy those commands and get access to them. And if you're using Singularity, it's honestly just one command to convert that Docker image to Singularity too. I'll add an example of that one in the presentation as well.
Thank you. Let me try once again. One final question for Zahra.
Yeah, I have a quick question. It seems that the RAPIDS provide pretty nice interface in Python, but, which could they be done in more complicated way with CUDA and C++ in that way? Is there any comparison if you do exactly the similar thing implemented with RAPIDS versus the in more native way, CUDA and C++ way? Like, is there a huge performance difference, or is it pretty much caught up?
That's actually a great question. And as you can imagine, yes, the performance is not similar. So you're adding that Python overhead for sure. But that's not something that we've ran those benchmarks yet. But it's a good point. It would be good to compare these to see how much of the performance hit you get once you move to the Python API. But a lot of this, like I said, is comparing it to the existing scikit-learn and CPU libraries today. But a lot if you want to use the C API too, that's also available. So if that's something that you want to integrate into your code, you can use that.
Okay, thanks.
Okay, great. Well, thank you again, Zahra. It was a very enlightening presentation. And we are very happy to see that these resources are actually now being used in production scale machines like Summit. So this definitely is another motivation for us to explore the use of these tools in earnest. So thank you very much for letting us know about all these capabilities that NVIDIA is providing to the community.
Of course.
Yeah. Ellie, I was going to add a comment to Zahra's answer to Jonathan's question, which I think was a really good question. We sort of presented in inverse order, so or maybe the right order. So we presented sort of the low-level tool set, you know, what we're doing with CUDA and then C++. So if you want to program at the low level, we're going to make that programming community, we're going to, arm them with all the tools and the best possible tools we can. But not everybody wants to develop at that level. Others want to just basically take the high level abstractions like scikit-learn and just go. And so for those programmers and developers, we want to enable them as well. So you really get to choose which way you want to, engage with the platform. And I think to the point that Zahra was making, while we haven't measured it, I think one reason we really haven't measured it is the performance relative to the baseline. CPU is so fast, and the programmer productivity is, almost as close to, 1x as you could get, because there's hardly any overhead. So maybe 1.1x the extra overhead to use the tool that way. We haven't even gone to the trouble of testing the lower level capability within that framework. And that's going to vary, I think, if we start to look at some of the HPC applications, but just because of the nature of the way they present themselves to the GPU.
Actually, I appreciate that answer. Actually, that's why I actually was asking the question, because is it worth of extra complexity as a native develop versus this more user-friendly developing environment? But I also realized that there's always performance pushing, always, even to use assembly. Okay, probably we don't use assembly anymore, but always, right? The cases like that. So do you have any actual cases that, out there, your users rather push, further with the native CUDA development instead of using all these more performance productive tools for that reason?
with the HPC applications, we certainly have compare and contrast. I don't know that we have any of that today. I will say this, that the gap is narrowing. So even if you're writing an HPC application, you know, less and less do you need to really develop at the CUDA level. It used to be, you know, if you didn't develop in CUDA, you were really giving up a lot of performance. But the tool chain that Tim briefed earlier has got, you know, we're at now 11. So back when we were at iteration 7, you know, the folks at NCSA would have seen a big difference in the CUDA performance versus what you could get with a high-level language. In fact, really, from a high-level language, you couldn't get anything. You needed to use directives. So that gap is getting narrower and narrower, but, you know, for an HPC application, there's still maybe performance you've left on the table. I think as Zahra was kind of briefing, the performance we're getting on these rapids, you know, at the high-level abstractions, there's overhead, but the performance gain is so high. You know, the impact on productivity probably just isn't there in general. Although, you know, you may have a use case, and in that instance, if you needed to get to the low level, those tools are available. But I think for the data science users, most of them would rather stay away from low level programming.
Yeah, thank you.